Welcome to the webinar on what is the PSD. My name is Jared Van Baren. I have been working at VR for just over 10 years in sales and marketing roles, and today I get to discuss with you the foundation of random vibration testing, the power spectral density, or PSD. We'll start with a brief introduction to random vibration and an overview of the terminology that will be used, and then we'll step through the process of generating a PSD. A quick disclaimer is this webinar is built to be an overview without a ton of math, so please note that there is a whole lot involved in calculating FFTs and PSDs that might not be covered today. In a few minutes, I will show you where you can dive deeper on our website if you wish. The goal today, however, is to gain an understanding of how the PSD is generated and how it is used in random vibration testing. Vibration research's core focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Our core values are collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. These values govern our decision making at a personal level and a company level. Many of our values are apparent to our customers when they receive assistance from our support group. However, innovation is most evident in our products. One thing I will encourage all of our listeners to do today is download our demo software. Version 2022.1 is coming out on our website, or is actually out on our website right now, but the public has not been notified just yet. But very soon we'll send out an email, so be sure you're subscribed to our email list to be notified right away. But yeah, 22.1 is already up there on our website, and you can download it, activate it. It's completely free. With that software, you can simulate sine, random shock, FDR, or field data replication tests with built-in resonances. You can try advanced features like Kurtosion, sign on random, and transient capture. You can automatically generate and print customized test reports. I like that one especially because it is super handy to create reports at your desk rather than having to be in front of a shaker system. You can also, speaking of shaker systems, you can size a shaker to determine if it can perform a specific vibration or shock test. And then just a general gain of knowledge or understanding on your control software when it's not running a test. So yes, download it, activate it, use it. It's a beautiful thing. One more plug I'll throw in there is that you can request to demo our hardware with software installed to make sure you like it and get a feel for it before committing to any sort of purchase order. So in this webinar, we will discuss the foundation of random vibration testing, the PSD, the power spectral density. So when we talk about sine testing, it's not a very realistic form of test. It's a great way to characterize the frequency response of a product or DUT, device under test, to a given input, but it does not relate well to the real world. On the other side of this is random. Random randomly excites all of the frequencies at the same time, giving us a real world way of generating a vibration test profile. A fun way to remember the two that was once described to me was the piano key example, if you ever heard of that. In sine, you're hitting each key one by one all the way up and down, sweeping back and forth. In random, it's what my 4-year-old does at home by hitting every single key at once. So sine, hit one by one going up and down the piano, and random, randomly exciting all the frequencies or keys at the same time. Almost all real world environments are random with a few exceptions. So notice I didn't say replay or replicate there. It's a random environment that is relatable to what the product will experience in the real world. We call it random because it's exactly that, random. I cannot use any measurement at one time to predict what has happened or what will happen in relation to the peaks and the frequencies that will happen next. It is non-deterministic and non-repetitive, as I state here in the slide. In the case of a random vibration test, our random vibration is very stationary. So what does that mean? It is stable random. If I am running a 5 to 2 kilohertz 2Gs RMS test, the overall amount of energy averaged over a period of time will be what? That's 2Gs RMS. It will be very, very stationary. A non-stationary test has energy shifting rapidly back and forth throughout the test. I suppose I should define GRMS too, which is the total acceleration content of a random vibration test, or the area under the curve of your random vibration test profile. So G is the unit of measurement for gravitational acceleration. RMS stands for root mean squared, which is a statistical measure of magnitude of quantity that has variation. So to sum it all up, random tests result in a more real world test because the random signal can simultaneously excite a wide band of frequencies similar to that of the real world. The excitation the DUT, or device under test, experiences in the real world is most likely not purely sinusoidal. Therefore, it makes sense that the testing that we do is not purely sinusoidal. So random testing allows multiple resonances and responses to be excited across a wide range of frequencies. At the same time, this provides not only the excitation of the individual resonance, but the interaction between multiple resonances and the effects on the device under test. A few quick definitions before we go further. So GRMS we defined in the previous slide. FFT, the fast Fourier transform, that's a computer method of shifting data from the time domain to the frequency domain. And the fast Fourier transform is exactly what it sounds like, a faster version of the Fourier transform. Windowing is a method that shapes the data being used to generate or calculate an FFT. Frequency resolution is set by a number of analysis lines to generate both a PSD and an FFT for the FFT calculation. Averaging refers to a method of combining a series of FFTs to generate a PSD. And G squared per hertz and meters per second squared per hertz are the units for an acceleration spectral density plot, where X axis is frequency and Y is G squared per hertz. So a few quick definitions there before we move on. The main graph or values that we use to define a random test and to observe random vibration is the power spectral density graph. In vibration analysis, PSD stands for the power spectral density of a signal. Each word represents an essential component of the PSD. In the previous graph, it is called an acceleration spectral density because I am defining in terms of acceleration, but the typical graph is called the PSD, or power spectral density. The name power spectral density does not include the measured quantity. So engineers sometimes replace the word power with the name of the measurement. For example, they may refer to the PSD of an acceleration signal as the ASD, or acceleration spectral density. And the PSD is an average power over some period of time. So let's define power. Power is the magnitude of the PSD, and that's the mean square value of the analyzed signal. It does not refer to the physical quantity of power, such as watts or horsepower. However, power is proportional to the mean square value of some quantity, such as the square of current or voltage in an electrical circuit. The mean square value of any quantity is the power of that quantity. So if we look at the blue image on the right, the mean square value, or power, is a convenient measurement of signal strength. For example, this image displays the vibration time history for a car's floor panel measured by an accelerometer. The mean square value equals 0.0053 g squared. And the root mean square RMS value equals 0.073 g. The signal's average amplitude cannot be specified by the mean value because it is near zero. However, we can square the signal, which results in a positive quantity. Then we can compute the mean square value. To obtain a linear value, g in this case, we can take the square root of the mean square value to obtain the RMS. The PSD plot can be created by an infinite number of waveforms, but when a PSD is defined, the GRMS will not change. This allows engineers to match a PSD to a specification and determine if the GRMS is as required. They can also use the GRMS to compare two PSD plots and verify that they are measuring the same amount of energy. So then spectral, that's the PSD is a function of frequency. It represents the distribution of a signal over a spectrum of frequencies, similar to a rainbow that represents the distribution of light over a spectrum of wavelengths or colors. So we're moving into the frequency domain and looking at broadband excitation of various frequencies for a period of time. So that's where spectral comes in. If we look at the blue traces again, it's difficult to determine the resonant frequency values from the signal's time history on the left. However, the peaks in the vibrations frequency spectrum clearly show these values on the right. So then lastly, density, that's the magnitude of the PSD is normalized to a single hertz bandwidth. For example, for a signal with an acceleration measurement in unit G, the PSD units are G squared per hertz. So that G squared is the power and the dividing by hertz is the density. Because we are normalizing this from a power spectrum into a PSD by dividing by the bandwidth of the test. The magnitude of a signal's frequency distribution depends on the number of frequency bands in the distribution. If we look at the lower right here on the slide, the frequency spectrum of a car vibration signal is computed with 3 different frequency bandwidths. The squared magnitudes of the spectra are proportional to the frequency bandwidth. To overcome this variation, the PSD divides the squared magnitude by the frequency bandwidth to provide a consistent value independent of the bandwidth. The definitions I just rattled off earlier were taken from the random testing course in the PSD section. You can find this right on our main site or go to vru.vibrationresearch.com. This is a really helpful site that goes further in depth on topics such as the one that I am discussing today. It offers practice exercises, instructional videos, and personalized learning dashboard that allows you to study at your own pace. And we tackle everything listed here and then some with the glossary and the knowledge base, sign testing, random testing, preventative maintenance, multi-axis, calibration, and a lot more. Yeah, so once you complete a course, you can take a quiz. If you pass, which you can take more than one time, you download your certificates, you can send them to your manager, you can print them out, tape them to your fridge, post them to your LinkedIn profile as an accredited course. This is a pretty cool option. So VRU is a very helpful tool. So a quick little shameless plug there for VRU. So how is the PSD created? Generating a PSD is pretty complex when you think about it. We're taking Gaussian time domain input data. That's a random waveform being generated by our controller, sent to the amplifier, then to the shaker, and being measured by the input signal. So that data is coming in and is divided into frames. And the width of the frame is set by your overlap percentage, lines of resolution, sample rate, and your degrees of freedom that we define for the test. Then for each frame of data, we calculate an FFT, which converts us from the time domain into the frequency domain. Then we square our FFTs to get into a power spectrum. Now we have G squared versus frequency, and then average each one of those power spectrums together until the desired degree of freedom is achieved, or DOF is achieved. So what does that look like? So you move into the next slide here. Here we have a 5-second random waveform. This data is difficult to look at. There's no real valuable information that can be observed from this graph. Maybe that the peak acceleration is at or near 30 Gs. It's difficult to determine much more than that from this particular graph. So in order to have a better understanding of what is contained in the data displayed, we need to convert into the frequency domain. There are two calculations used to view random data in the frequency domain. The fast Fourier transform results in G's versus frequency plot. This is useful when looking at a single frame of data. There's no averaging or normalizing applied to the resultant plot. When playing through a time history and looking at the FFT, it is possible to observe small and fast changes to the overall frequency spectrum. Then there's a second method, which is power spectral density. This is a combination of FFTs that are windowed and averaged together. This provides a slower changing graph that characterizes the amount of energy inside a particular frequency bin for a period of time. And that period of time is set by a parameter known as degrees of freedom, or a lot of times you'll see this just DOF, DOF. So degrees of freedom could be closely related to the amount of time that is being averaged into a PSD. The first step to generating a PSD is to generate a series of FFTs. In order to do this, the data must be divided into frames. Each individual frame will result in a single FFT. The average series of FFTs will result in a PSD. Lines of resolution and sample rate determine width of each frame. There are 2 samples per analysis line. In this case, the recorded time history was sampled at 8,192 hertz, and the lines are set to 4,096, resulting in a frame width of 1 second. If the analysis lines were changed to 1,024, the frame width would be 0.25 seconds. So when calculating an FFT for a single frame, a windowing function is applied to the waveform. The FFT is a circular algorithm, meaning that the 2 endpoints of the frame of data are interpreted as though they were connected together. We are looking at random data. Most likely the beginning and end point for the individual frame is not the same. If the beginning and end point of the frame are not the same, it results in a large transition between the 2 points, which causes a large amount of high frequency energy to be included in the calculation. So think of a terminal peak shock pulse. The sharp transition from the peak amplitude to 0 acceleration generates a much larger amount of high frequency energy than a smooth pulse like the half sine. For the FFT, that sharp transition between the beginning and end point is a discontinuity. That high frequency event affects the calculation, called spectral leakage. The windowing removes emphasis on the discontinuities and reduces the leakage effects. In a perfect world, the real data would have a starting and ending point that are identical in every frame of data. This would minimize or eliminate any leakage. Because this is not the case, we have to minimize the leakage effects by utilizing a windowing function. So each window function has different characteristics that make them more suitable to various or certain applications. A window function is evaluated by 2 key components, the side lobe and the main lobe. In the example above, the Hanning window is used. It has a very high, wide main lobe and low side lobes, essentially reaching 0. This means that there's little to no discontinuity between the beginning and end point of the frame, which results in very accurate frequency measurements. The Hanning window is used in the vast majority of cases because it provides good frequency resolution and minimum discontinuities and therefore leakage. Other windows may be more appropriate for other situations. For instance, a flat top window would provide better amplitude accuracy with reduced frequency resolution. A Kaiser-Bessel window may be used when two waves are near each other in frequency but have drastically different amplitudes. Window time data is used to calculate the FFT. Basically, the FFT is a mathematical function which transforms the signal from the time domain into the frequency domain. This linear transformation gives us the ability to observe the frequency content of the time history waveform. There are many use cases for the FFT in signal analysis and processing. Most importantly, it shows what frequencies are present in a signal and at what proportion. This can be used to determine what frequencies are being excited by a particular section of time, the peak acceleration of that particular frequency inside of a windowed frame of data, the distribution of peaks and harmonic content, etc. There are a few notes that must be made when calculating the FFT. There are certain factors that can be applied to the windowing function for different purposes. If the goal of this process was to simply generate an FFT, a weighting factor to ensure 1G peak of the time domain data is equal to 1G peak on the FFT. So when generating a PSD, the window function is normalized to preserve the input power. Yeah, quick slide on the averaging the FFT. The individual FFTs are then averaged together. As more frames are averaged together, the accuracy of the PSD continues to improve. This is directly related to variance, a statistical property that describes the hashiness of the data. As variance decreases, accuracy increases, and the overall PSD will look much smoother. Simply put, as we analyze more FFTs, we analyze more of the time domain and get a better representation of the actual time domain content. The next step in the process is to square the averaged FFT to calculate squared magnitude or power. The mean square value, which is power, is a convenient measure of the strength of a signal. The average amplitude of a time signal cannot be specified by the mean value since it is essentially zero. Instead, the signal is squared, resulting in a positive quantity, and then the mean value is computed. The final step is to divide the averaged squared magnitudes by the sample rate. This normalizes everything to a single hertz and creates an acceleration spectral density or power spectral density graph. The acceleration unit is in G squared per hertz, and G squared is the squared magnitude of power, dividing by hertz to normalize on a single frequency. So using the PSD, I can clearly see the response of the product over a period of time. As more frames of data are averaged together, the variance or hashiness of the PSD decreases and becomes smoother. For a more in-depth look at variance and methods of PSD smoothing, watch our webinar on instant degrees of freedom, or IDOF. This is a patented feature from VR that effectively reduces the variance or hashiness of a displayed PSD trace, which creates very smooth PSD traces. It's the only truthful and effective method of displaying a smooth PSD trace. The PSD shows the average energy at a single frequency over a period of time. This period of time is determined by an analysis parameter called degrees of freedom. The higher the degrees of freedom, the more frames of data that will be averaged together. More degrees of freedom means more frames of data are being averaged together, which creates a longer period of time to acquire. There's a technique called overlapping, which ensures that more of the data is being used to generate a PSD. So more data being used to generate that PSD. In the first example, there was 0% overlap between the frames of data. This means that the data being reduced by the windowing function is not being accounted for. A 50% overlap means that there would be 0.5 seconds between the start of each frame, and 50% of each frame would overlap with the frame before and after. This means that for the same set of data, 9 FFTs would be generated, and those 9 FFTs would be averaged together to generate the PSD. Next, we look at how the PSD is spaced in lines of resolution. These lines are linearly spaced. So when we set up our lines of resolution in random, there are 2 variables that are calculated based on our settings. The frequency resolution based on the number of lines and the sample rate. And you will get an update interval, which is how the graph and the PSD calculation is updating. And you can adjust these settings so that you get the right settings for the test that you are trying to run. When we talk about lines of resolution, a lot of users like to use lower lines of resolution so that they can achieve degrees of freedom faster. This is pretty common for short duration random vibration tests. So what's the big deal? Well, the problem is you run into that you do not have enough degrees of freedom to appropriately resolve the peak of a resonance. The amplitudes you measure are significantly less than the actual amplitudes that are being excited. So this is a measurement error problem. If I use too few degrees of freedom, I may end up having significant discrepancies in control and demand. This example on the right shows that when you increase the lines of resolutions, you can see the true peaks are significantly greater when you measure with the appropriate resolution for that resonance. Another note I had is that Mill Standard recommends that you have at least 3 lines within the resonance. So a little about statistics. There's 4 in vibration testing that we primarily concentrate on. You only see 3 there, so I'm getting to the 4th after in the next slide. The first one is your mean or mean square value, which is where we get power. Second is variance. It describes the hashiness of a signal. You've heard me use that a few times already, or variability of the signal around the mean. And skewness is the measure of the asymmetrical spread of a signal about its mean value. And the 4th is, you guessed it, kurtosis. This is the 4th statistical moment that describes the peakiness of the data, or the probability of the peak occurring in a set of data. If we look at the right side here, we can see 3 different time history waveforms. First has a kurtosis value of 3, the second of 10, and the third of 20. The first one looks like a pretty standard random vibration, not too extreme and relatively repeatable. Next in red, we have a higher probability of higher peak accelerations occurring in my time waveform. Final in blue is pretty extreme. These all actually have the exact same PSD and GRMS. All 3 would look identical in the PSD analysis. So there's a few ways to evaluate different tests and running different tests with kurtosis and verifying that you are in fact not only getting those peak accelerations in the control trace, but also driving them through your product into the resonances, which is the true key of adding kurtosis into those vibration tests. So we conclude this webinar by summing up what we discussed. We introduced a key component of random vibration testing, the PSD. We talked about a brief introduction into random. We talked about some key terms. We stepped through how the power spectral density is calculated in the meanings of the words power spectral and density. Finally, we reviewed windowing, overlapping, degrees of freedom, and lines of resolution. So please type in the chat if you have any questions or email vrsales@vibrationresearch.com. I will follow up with a presentation with a link to the recording, hopefully this week yet. It should be live on our website. I got your emails through the registration form, and I will hopefully email that out to you this week, perhaps next week, depending on how long it takes to process the recording. Thank you very much for listening today. We value you greatly as a customer and look forward to future conversation or meetings or support with you. So have a great rest of your day. I'll hang around for a few minutes for some questions in the chat box, and I will try to respond to them in a timely manner. So thank you very much.